Okay, so today's lecture is basically a crash course in deep learning terminology, right? So I know that a lot of people have come to this class with, part of the requirement for the class was some sort of introductory machine learning knowledge. Last time we covered like the old school stuff, the basic perceptron and so on. What I want to talk about today is just like a whirlwind overview of deep learning architectures, deep learning terminology, with the understanding that probably there are people in this room that know this so much more than I do, right? So I'm sure that if I make any mistakes, people will step in to tell me something that I missed, right? My goal is not to teach you an entire deep learning course in, an hour, right? But to give you the names of things so that when you encounter these words in a paper, instead of kind of bleeping over them, you kind of understand a little bit what they mean, right? And of course, to really get into, how do I decide on the right architecture and build these networks? That's where you take a full-on semester-long deep learning course, right? This is just kind of like an overview, right? And like I've said before, my goal is not to dwell a lot on the real nitpicky details of architecture and optimization and so on, but to more concentrate as we go on the big picture of what is the philosophy behind these networks, how they work, how people use them, right? So with that, let's launch ourselves in. This is going to be another kind of note-heavy lecture with a few computational things at the end. So just a refresher from last time, right? Let me just refocus this camera a little bit. It's ironic that this camera has this autofocus that is always better if I turn it off. So there's a image processing problem for you. Okay, so kind of where we left off in the last lecture was this fundamental idea, right? We have our input. This goes through some sort of model. The model has a lot of parameters, which we're going to call theta. The model produces some sort of output, which is like a prediction. And then we have some sort of a loss function, which relates the predictions to the ground truth, right? And our goal is to find the parameters theta that minimize the error, right? Or come close to minimizing the error. Now again, as we talked about before, these thetas generally take the form of a bunch of weights and biases on individual neurons, right? So kind of what we talked about before was I have a vector of, inputs. Say each of my inputs is n-dimensional. I dot product this vector with a bias and a bunch of weights, and that gives me the output of, one neuron, basically, right? And we kind of talked about how, the big picture goal is to use some sort of gradient descent, right? So gradient descent is the way we numerically optimize this function because analytically, taking the derivative and set it equals 0 is not something that is really possible to do, right? And so let's just take a very simple example of a network that has like just a couple of neurons in it, right? So here's a simple example. Let's suppose that we have a two-dimensional input, and these guys go into a neuron. Let's call it F. And so let's also suppose that we have a bias, right? And then what comes out of F, I multiply by another weight, and it goes into a neuron G, and then I have a bias for this term, and then I get my output, okay? So it's like saying there are really 5 parameters in this neural network, right? I've got, theta 1 multiplying this bias, theta 2, theta 3. The output of this neuron gets multiplied by theta 4, and then this bias is theta 5, okay? And then I could imagine that I also have to specify, remember that I'm not just necessarily, I guess I should be clear, I also need to activate this neuron, so I should have been a little bit careful here, right? So I do this kind of dot producting, and then I process that through some sort of activation function, right? So each of these neurons here has an activation, right? So for example, let's suppose that in this guy here, just to kind of make it different, let's suppose I'm using, what did I say for this? Tan H, hyperbolic tangent. And for this guy, I'm using sigmoid. these are the activation functions for each of the neurons. And then let's say that our error, our loss function, is basically the mean squared error, which is going to be 1/2 the sum of the predicted outputs and the true outputs, okay, for however many samples I have. And so if I think about, kind of expanding out what does one of these loss function terms look like, what's actually happening is I have basically, for one term, let's drop the I for a second, then the loss is like, this is the truth, and how did I obtain this yi? Well, I basically took the sigmoid of theta 5 plus theta 4 times the output of this neuron, which is the tan h of theta 1 plus theta 2 times x1 plus theta 3 times x2, right? So now I can explicitly write down how does each of the training samples contribute to the loss function, right? So I pause and ask questions or comments about this so far, right? Okay, so now what I need to do is to basically find, if I want to take steps along the gradient, I have to find the gradient of this function with respect to each of the theta parameters, right? And everyone knows calculus, so you should be able to do that. Now, one of the great things about neural networks is the fact that the finding the gradient part has a very nice structure that comes from the graphical nature of the neural network, right? So the elegant observation is to basically write this function in a slightly different way, right? So let me kind of be a little bit more explicit. What I'm going to do is I'm going to say, OK, I'm going to let, and let me just kind of move my paper around a little bit. So I'm going to let, say, the output at the F neuron be, or basically the input to the F neuron is theta 1 plus theta 2 x1 plus theta 3 x2. Arguably, I could have given these better numbers, but it's all right. And then the output of the neuron is basically, if I think about f of what comes in, is just the, what did I say, tan h function, right? And then I can say, well, what is the input to the G neuron, right? The input to the G neuron is, as a function of whatever comes into it, is theta 5 plus theta 4 times x. And then the activation of the G neuron is, what did I say, the sigmoid function of whatever comes into it. And then the error function that comes out, we already know is just the error of y hat is 1/2 y minus y hat squared. Okay, that's like one of the error terms. And so the nice thing is that I can take this here, which is basically my error, and I can write it like the, what's the word? Composition of all of these independent functions, right? So my error is actually this e function of the sigmoid function of the zg function of the f function of the zf here, right? And so that's basically one piece of the loss term is this basically nested parenthetical, right? The reason I did it this way is that now we can use the chain rule to make the gradient computation easy, right? Or at least make it written in an easy way, right? And this is where we're going to get a lot of efficiency out of it, right? So if I wanted to compute the gradient of this constant with respect to one of these variables, right? So say for example, I want to do it with respect to theta 1, okay? Well, I would say the gradient with respect to theta 1, and I guess I can kind of try to keep all this on the board at the same time. Move down a little bit. All right. So gradient with respect to theta 1, well, I'm going to kind of go from the inside out, right? And I'm just going to call this, I should maybe call this just S for e's, right? So it's like saying, well, first I take the gradient of partial with E with respect to S, then I have the partial of S with respect to ZG, then I have the partial of ZG with respect to F, and then I have the partial of F with respect to ZF, and then I have the partial of ZF with respect to the thing I actually care about, which is theta 1, right? That's the chain rule. And the same way, if I wanted to take the partial of E with respect to theta 2, it would be almost exactly the same thing, right? I would have to work my way backwards along the chain until I got to the partial with respect to theta 2. And the thing to observe is that all of this stuff is exactly the same except for the last term, right? So all this stuff is the same. So I definitely have to make sure that when I'm computing these derivatives that I save these intermediate computations and pieces of them in order to reuse them, right? The whole point is not to have to recompute this fresh for every derivative I want to take, okay? And then the nice way of looking at it is that since each of these functions is very simple, the derivatives are also very simple, right? So for example, the derivative of E with respect to what comes into it, this y hat is basically, s, right? So this is going to basically be minus y minus s of whatever comes in, right? This is the derivative of this. The derivative of the sigmoid, right? This is just going to be whatever we call, sigmoid prime. This is, something that's easy to compute. The derivative of this with respect to its input is just theta 4. The derivative of this with respect to its input is whatever the, derivative of this is. Also an easy computation. And the derivative of this with respect to theta 1 is just 1. And with respect to theta 2 is just x1, right? So each of these intermediate steps is super easy to compute, right? And then I just multiply all this stuff together with the chain rule, right? And so one thing to kind of keep in mind is that I need to preserve a lot of stuff along the way to reuse it later, right? So for example, I definitely need to make sure to preserve, like, what is the input to this neuron, right? And what is the output of that neuron? I have to kind of make a table or a, memory of all these intermediate activations. And this is kind of why there's this kind of forward-backward element of the algorithm, which is that first I go and do all these forward calculations, I keep a bunch of that stuff, and then I go back to figure out the gradients by kind of backwards propagating the stuff I computed all the way down to the root. And that's why this algorithm is called backpropagation, okay? And so basically the idea is to do that, right? So, so we have to keep track of neuron inputs, outputs, and errors to elegantly reuse computations, right? And so the general idea is called backpropagation or backprop, which I'm sure that if you take an ASR machine learning course, you've heard this word before. And my goal today is not to reteach you backpropagation, just to remind you what it is, right? So again, the idea is that if I want to compute the derivative with respect to theta 1, what I would do is I would say I have an error that comes from, the output, right? This is basically the output error. And then I multiply that by derivatives of activation functions. and then I multiply it by inputs to the various layers, and then I have another activation function derivative, and then I have another input. Again, let's not worry about this over much. Like, I'm not going to ask you to do backpropagation on, manually or anything like that. I just kind of wanted to revisit, like, why it's actually reasonably interesting that this is a good idea, right? So, normally taking derivatives with respect to a bunch of parameters for an arbitrary function is not usually so well structured, right? The nice thing about this multi-layer thing is how nicely the structure helps you out when computing the derivatives, okay? And there are a zillion tips and tricks to try to make backpropagation work better, right? So there's like a lot of numerical computational stuff under the rug that you need. It's not like you just kind of like run this algorithm as is and it works the first time, right? So for example, one of the critical things, right? So let's say lots of rules of thumb to make this work right? So for example, a key one is when I'm doing this gradient descent, I have to start from somewhere, right? And so there are many standard choices of how do you start, right? So should I just randomly assign all the parameters to random numbers, or should I start at 0, or should I look at some data and normalize my data and then assign some numbers randomly? Again, lots and lots of ways to do it. There are standard ways to do it, right? So normally when you're doing this in a piece of code, it's just like one line to say, how do you initialize, right? One of these standard things. And then there are many, so I think I mentioned last time, learning rate is an important one, right? So every time that I compute this gradient, I'm not just computing it once, I'm computing it many times and taking little steps along the gradient, and I have to make a choice at every turn about how big is that step going to be, right? So the step size of the learning rate is an important thing, because if I do it too big, I'm going to overshoot, and if I do it too small, it's going to take forever. And so that number also may get tuned over the course of the process. There's like a schedule to how do I change the learning rate. Again, something that you just like kind of plug in as a standard thing, right? And then also, there are lots of reasons why. So first of all, now we see from these terms why we moved away from basically like a signum function, like a step function as an activation function, because we're going to need to take derivatives of things, right? And so that's why we moved to these smoother functions, because we know we're going to need their derivatives. And so a lot of, kind of deep learning theory has to do with kind of trying to keep the whole network differentiable, right? Because if it's not differentiable at any point, then you have a problem. And so just a kind of recollection that these functions basically look like, a smooth function like this, right? This is kind of like a picture of a tan H function, right? But then this too introduces its own problems, right? So this is like the worst picture of a tan H that you could make. So let me make another one, because it should be nicely going through 0. Okay, so tan H kind of looks like this. And so it has an asymptote at plus and minus 1. So one numerical problem that has been a problem for a long time is what are called vanishing gradients, right? So the idea is that suppose that I have a guess for the parameters that is really way, way off, right? So instead of being in this nice area of the curve, I'm like way out here where the error is so bad. But if I think about it, this function is basically flat. So here, the derivative is approximately 0. And it's approximately constant the further out I go, right? And so this could generate problems that are called vanishing gradients, right? Because once I start to introduce very small numbers and I multiply a ton of these very small numbers together, it could be that the step I take in the gradient is like virtually 0 and my function doesn't move, right? So there's a lot of effort spent on how can we make sure this kind of thing doesn't happen in our network, right? And again, people have discovered kind of standard ways to do this. And kind of conversely, there's something called exploding gradients, right? So for example, if I have a ReLU function, right? So this is like tan H, sorry, and this is like ReLU. So here, the further out I go, the bigger the gradient gets, right? So I may have some numerical problems with having like huge gradients when the function is way off, right? So that could also be a problem. Exploding gradients. And so there are ways to kind of combat those kinds of problems. So one way of doing it, for example, is a kind of normalization that we'll talk about in a second, like how do you normalize the batches of data that come in, right? Okay, so yes.
Isn't the gradient constant here?
Isn't the gradient constant here? Here?
Or really?
Oh, well, actually, that's a good point. The gradient is constant. Yeah, okay.
Just be one or
Yeah, okay. Well, okay, so maybe this, so I should say that the vanishing gradient problem can happen anytime. This is kind of like a separate, put this somewhere else. Like exploding gradients can happen with different functions, but you're right. I misspoke. This is not the problem with ReLU. ReLU would be okay with this, but there are probably other problems, right? Yeah, sorry about that. And so there are lots of ways to do the optimization. And so typically when you instantiate a neural network and say optimize, almost always you're going to just select some default parameters and you're going to select some default optimizer, right? So one popular optimizer is called ADAM, right? You probably use adaptive moment estimation is what it's called. So, typically there are default, options for optimization. For example, one well-known one is called ADAM, which is adaptive moment estimation. All of this stuff is basically like some flavor of gradient descent under the hood with a bunch of different kinds of tricks to make it perform numerically well in practice, okay? You don't really have to know the details, the gory details of how this works. Now, if you are interested, just as a side note, I always encourage people to take like a numerical optimization class or a numerical methods class in the math or applied math department to really understand how do you translate these concepts that you learn in calculus and linear algebra and then make them work on a digital computer in practice, right? So there's a big, interesting gap between what you learn, like take the derivative of say equals 0 or take the inverse of this matrix versus how do you do it on a big computer with a huge matrix, right? So I definitely encourage you to take those kinds of classes if you have the chance in your schedule. Okay, so one other thing I wanted to mention before I kind of forget is that, I mentioned gradient descent, right? So true gradient descent would imply that when I compute this error function, like over here, so like going back to this, so true gradient descent would be that I actually compute this term every time I take a gradient step, right? Meaning that I have to use all the samples every time, right? In practice, for numerical reasons, if I've got like millions of samples, it may be such a huge pain to compute this for all the millions of samples all at once, right? So kind of another thing to know about is that, in practice, we do basically optimization in what are called batches. Which means I take all of my training data samples and I chop them up into a bunch of smaller batches, right? So these are all my training samples. Each kind of small thing is called a mini batch. To be honest, I'm not exactly sure why they don't just call it a batch. But anyway, so the size of this thing is what you see called the batch size, right? So, basically, we also typically in optimization set a batch size. And then I keep on iterating through these non-overlapping batches until I've gone through all the data once. And going through all the data once is called an epoch, right? So then I go through all the kind of non-overlapping batches once, and that's what's called an epoch of training. And so when you do some sort of training, and I'll show you an example in just a couple minutes, you'll see basically it's like epoch 1, epoch 2, right? And that means that I'm going through all the data once, but that epoch is split up into batches or mini batches that have got some size that was set somewhere in my optimizer, right? And in the limiting sense, if I have mini batches that are of size equal to 1, then you have what's called stochastic gradient descent, or sometimes called online learning, right? So batch size equal 1 is called stochastic gradient descent. or online learning, where that's basically like saying, I just randomly choose a sample, compute the gradient just for that sample, and then I just loop through all the samples, right? And again, from an optimization point of view, there's lots of work on, what is the right way to balance the size of the batch with convergence and all this stuff. And you could take a whole class on this kind of thing, right? But that's not this class. Okay, so, and one thing I also say is that, one of the advantages of doing it with this batch size is that then you could parallelize your batch computations, right? So all this stuff is done on these parallel processing GPUs, and so the idea is that I could split this stuff up and farm out the computations to a bunch of different GPUs and then come back to compute the cost function, right? So again, it's all about how can I make this stuff run on kind of, my typical modern GPU hardware. I can tell you, I learned neural networks when I was in grad school in probably the late 90s, right? So I learned backpropagation. I did backpropagation. This was prior to GPUs really existing, but no one was talking about batch sizes and epochs and stuff like that because it wasn't possible, right? So now it's like, just automatic. Okay, so I want to talk a little about neural network architectures. Let me pause and ask any questions or comments about what I said so far. Did I say anything wrong or misleading? All right, that's good. Okay, so, so far we've really only been talking about like one network with 2 neurons, right? In practice, networks have like millions or billions of neurons, right? And these neurons are arranged in different ways. And so that's called the architecture of the network. We have to make a choice about how do we arrange these neurons to solve our problem, right? And again, there's no necessarily right answer. I mean, there are certainly rules of thumb for which kinds of architectures you should use for which kinds of problems, but you're free to play around with how many layers and how wide the layers should be and so on, right? And so the most kind of common network architecture is called the multi-layer perceptron. So this is going to be basic network architectures, right? So this is called the multi-layer perceptron. AKA the fully connected network. And so how would that work, right? So suppose that I'm trying to make a neural network that classifies, little pictures into cats and dogs, right? So what I would do is I would take my input. So say this is my input. And since I'm an image processing guy, I usually think about this like an image. Then the first thing I need to do is kind of make my, first layer of neurons, right? This might be what's called flattening. So I take my grid of image pixels and I turn them into a long vector of image pixels, right? So a 100 by 100 image becomes a 10,000 long vector, right? And then I start making these intermediate layers. And a fully connected network means that every input is connected to each of the outputs, right? So you immediately realize that you probably should have drawn fewer neurons. But you can see how it goes, right? And finally you, okay? Now, one thing I'm not even drawing in this picture is the biases, right? So, implicit to this also is there's some other bias term that's coming into each of one of these neurons in the hidden layer that's multiplying by 1, right? If I think about one of these things as, well, yeah, biases are implicit in this picture, right? And then I might do this again, right? So then I might bring it down to a few more neurons like this with another fully connected layer, right? So this type of thing is a fully connected layer. And then eventually, I have to kind of get this down to one numerical output. And so each of these things here, each of these neurons, sometimes you'll hear called a unit, right? Just like one of these things is called a unit. And then all these things are weights, including the bias kind of implicitly. And so when I'm talking about how do I train the network, what I mean is that each of these lines has a number attached to it, which is the weight, plus the biases, which I'm not kind of picturing. And so even in this simple hand diagram, there's probably hundreds of weights that I have to automatically tune, right? So I've immediately constructed for myself a pretty challenging optimization problem, right? Now this is fairly common, this is like the way like a lot of classification algorithms start out, and you still will see, even if you're not talking about an entire network that looks like this, often you'll see like a fully connected layer, which just means that, I take one layer and I, fully connect it to the next thing, right? And so, as we'll see in a second, different programming languages will kind of, give you a little bit of a summary report of what kind of layer do I have at everything, right? Now, again, coming from a world of image processing, right? The next big innovation in neural networks was what's called convolutional neural networks, right? So, again, I guess not everyone here is a electrical engineer. Some of you may be computer scientists, right? But I'm a double E by training, and so I learned and I teach about spatial filtering in images, right? So the next kind of thing is what's called convolutional neural network, or CNN. And so the observation here is this is basically very related to digital image filtering. And again, just as a plug, so let me just look at my browser for a second. So if, since we're doing a lot of imaging in this class, if there's a point where you feel like you need to brush up on image processing, then I have a whole bunch of image processing playlists for you, right? So where is that? Right, so here. So, okay. I don't want to hear myself. So for example, if you want to kind of go back to like spatial filters, this lecture 6 on spatial filters will kind of tell you, crash course in dealing with pixels and so on, right? I'm kind of assuming, I guess I didn't make it a requirement for the class, but I guess implicit also is that you know something about what are pixels in an image, right? If at some point you're like, what is he talking about? Then I think that watching like the first like lectures, kind of 4, 5, 6 of this image processing class would be good kind of backup material. Okay, so what is a filter, right? So the idea is that I have an image, and then I have a little tile that I call the filter, and let's suppose this is like a 3 by 3 filter. What I do is I take this and I place it over a place in the image, and then I multiply corresponding pixels together and add them up, right? So basically I take, the filter coefficients, which don't change. I take the dot product with the image pixels where I am, and then I get a response, which is like a scalar. And so one of the first things that we do in image processing is talk about filters like this. So for example, if I have a filter like this is one of what are called the Sobel filters. I think about what happens if I center this filter on top of an image, right? So what this is going to do is if I have a strong edge in the image, right? So say the top of the image is black and the bottom of the image is white. When I put that filter over the boundary, then these elements here, the 1, 2, 1 positive elements, are hitting the white side, and the minus 1, 2, 1 elements are hitting the black side. And so I'm going to get a big positive number as my result, right? On the other hand, if I put that filter in the middle of a constant area, then the top part and the bottom part are going to exactly balance each other out, and I'm going to get 0, right? So the idea is that this filter is only going to give me some sort of a response when I'm sitting on top of this horizontal edge. And if I were to transpose this filter, then I could detect vertical edges. And if I were to skew it by 45 degrees, I could detect the diagonal edges, right? And so that's something that we talk about is like, what are good spatial filters in image processing to accomplish certain tasks, right? Now, the idea with a convolutional network is that we are learning such filters, right? So the idea is like, let's suppose that I have a 3 by 3 input like this. Right, so let's suppose I have a set of pixels numbered 1 through 9. what I could imagine is taking this layer and turning it into a layer of 4 neurons that are produced by centering a 2x2 filter over each possible area, right? So for example, this, let me just number these for my own ease here, right? So this neuron would basically be what happens when I apply the filter to 1, 2, 4, and 5. Then I click the filter over 1 notch, and now I'm applying it to 2, 3, 5, and 6 for the next guy. And then I have 4, 5, 7, 8, and 5, 6, 8, 9. And so kind of the idea behind a convolutional layer is, number one, I have a kind of a smaller sized set of coefficients. And number two, I'm basically learning this 2x2 set of parameters, right? This is my filter that instead of assigning those numbers to be a given digital filter, I'm letting the network tune those numbers to learn what the filter should be, right? That's called a channel, right? So the idea is that even though there are, I guess, it's too late in the day for me to count. Even though there are 16 lines in this diagram, there are really only 4 unique numbers because I'm applying the same filter at each of these positions, right? And then, the idea is that these are filter coefficients to be learned by the network. And I apply those uniformly to everything in here, right? Now, basically, I can learn a bunch of these filters in parallel. So each filter in neural network parlance is called a channel. So the idea might be that I choose to say, OK, at this layer of the network, I'm going to have a 3x3 by 10 convolutional layer, which says I'm going to learn 3x3 filters, and I'm going to learn 10 of them, right? I'm going to let the network figure out what 10 filters I should be using, OK? And of course, there's a zillion details about how this works, right? So for example, one thing that you noticed here is I went from 9 neurons to 4 neurons, which is probably not always what I want. So a lot of times I want to keep the size of the layer the same going in and out. And so the problem is that I can't really apply this filter wholly to any more than these 4 locations. So there's kind of a question about again, let's just talk about there's basically padding is a question. So I could apply the filter to more than this area if I were to kind of hallucinate a bunch of values outside of what I actually have, and I might just assume that all this stuff is 0 outside the box. In that case, I could legally apply the filter to any location I wanted and just get the results be 0. And that way I would have the same size input as the output, OK? And that's often, I think, what you want to do. Another thing that is an issue is what's called stride. So stride, again, when we're doing convolution in image processing, typically we're running that filter across the entire image, right? But there are sometimes reasons why maybe I don't want to apply the filter at overlapping areas, right? So suppose this is my filter. Maybe instead of having the things overlap, maybe I only want to have it overlap by half the filter size, right? So this is filter number 1, and then this box is filter number 2, and this is another one like this. So effectively, by having a stride that is more than 1 pixel, I am going to reduce the size of my output, right? So a lot of times, a common thing is to have a stride that reduces the spatial resolution while then at the same time increasing the number of channels that I'm learning, right? So again, it's a whole black art of how do you decide what to do there. And there are reasons why, I could even have a stride where I'm skipping, big chunks of pixels, right? I'm actually hopscotching over pixels that I don't want to talk about, right? And so again, these are all implementational issues that when you put a convolutional layer in, you just make some choices about your stride and your padding, right? So the idea here is that since I'm learning a bunch of different channels or filters, the hope is that the filters are going to learn something useful about the input, right? So for example, when I think about a network like a multi-layer network, right? So suppose this was a convolutional network and not a fully connected network. My hope is that convolutional layers kind of at the lower level are going to learn kind of low-level image processing stuff like edges and lines and stuff like that, right? And then as I move up the network, the idea is that now, since I'm kind of, I may be kind of making the what's called receptive field of the convolution larger, so that kind of by the time I get up to here, it's like saying, okay, well, here I've learned about edges. Now if I'm applying this to pictures of like faces, for example, maybe I hope to start now picking up like, eyes and noses and mouths. So by the time that I come up to this part, the features are going to be, or the channels are going to be responding to things that are more like high-level semantic image features instead of low-level edges and blobs, right? So again, that's kind of like, that was a huge innovation in neural networks, was the idea of a convolutional layer. And I guess the third major thing that is kind of like neural network architecture is what's called a recurrent neural network. And I will say up front that even though it is clearly important for a lot of machine learning, when I looked at what I eventually wrote up my notes on, I don't think I'm going to be using recurrent neural networks that much in our lectures, but I thought I would just say something about it anyway, right? So this is called an RNN. Typically, this is something that you would use for basically like time series data, right? So if you're talking about an audio signal or a speech signal, or if you're, recurrent neural networks are definitely used in things like text prediction, right? If you're thinking about the way that ChatGPT produces output now based on what output came before, oftentimes you can do that with a recurrent neural network. And so the basic structure of that is like saying, okay, let's suppose I just have some sort of simple network like this. So each of these neurons here maybe is not only taking the output from this input, but also I kind of put it through a delay block, and I feed in the previous input, or the previous output into this neuron, right? So I may have a little thing here that this is also a delay. And then this delay may go into both of these inputs as well. So this is like saying that not only am I processing the inputs, but also I'm processing a delayed version of the outputs, right? And so kind of one way of thinking about this is that, for example, when I'm conditioning on, I'm talking about like generating text in ChatGPT, for example, right? What I want to do is I want to generate the next word, and then I want to remember what that word was as input to the next word prediction, right? So I'm always kind of like thinking about what did I output before as another input, right? And so as you can imagine, drawing these kinds of networks is a pain because you have all these kind of like arrows going back the other way, right? And so again, if you've heard of like, an LSTM, right, long short-term memory, that's an example of a recursive or of a recurrent neural network, right? We're not going to talk a ton about that stuff in this class. I may come back to it at some point just in passing, right? But I think in terms of like the big three types of networks are like multi-layer perceptron, convolutional neural network, recurrent neural network. That's going to be most of everything that you would ever see in reading papers in this area, okay? Okay, so, all right, let me pause and ask questions or comments about anything. I have a couple more terms and stuff I want to say, so if I didn't get to your favorite term, give me 5 minutes. All right, so a couple other things. So other terms that may be in the literature, right? So a big issue is what's called batch normalization. And so we talked about this issue of like vanishing or exploding gradients, they could be a problem, right? So it turns out that one of the easiest ways to kind of combat these problems is that if I have a mini batch of inputs coming in, so let's say I have n elements in my mini batch, what I could do is I could estimate the mean and the standard deviation. This is like the sample mean and variance. And I guess I'm doing this in 1D just for ease of explanation. And then what I could do is I could take each of these xi's, subtract off the mean, and divide by the sigma, right? This is going to basically should be zero mean unit variance. And then I could, so this by itself is kind of what you'd call some sort of normalization, right? So this way, I'm taking whatever wild variation there may be in the inputs and kind of centering them back down so everything is like nicely well behaved, right? And then I could also put this through a little, couple extra parameters like beta and gamma to produce a yi that is like scaled. So if I call this xi hat. And so these parameters here could be also learnable. So it's basically like a kind of a rescaling, right? All I'm doing is I'm moving the mean and variance around of my input to make it better conditioned for what happens in the network in the next phase, right? And there are lots of ways of how do I choose, how do I do this, right? And what makes good sense for a network. And again, to me, this is, not like super exciting to talk about. Like it's just kind of like, obviously, maybe you want to rescale your input somehow, but then there's all sorts of like secret ways to do it the right way. Definitely, one thing that I was surprised by in doing my review for this class was how much innovation you could get in terms of like improvements in an algorithm just by using like a slightly different normalization, right? Which is like, in my opinion, not necessarily super like mathematically well principled. It's just like, okay, we tried this normalization and now it works so much better, right? Now we're going to use this from now on, right? So that's the way a lot of developments in certain areas kind of developed. So you'll definitely cross, sometimes you see all batch norm, right? How do I do the batch norm? Dropout is another word that you're going to hear. So dropout just basically means that, suppose that I have a bunch of, weights that I've learned. Suppose I learned, for example, that the weight on this vector should be, suppose these are the weights that I learned on a certain set of arrows. So if I have like, 25% dropout, what that means is that I basically just like choose one of these randomly and set this equal to 0. Right? So going forward, it's like the output of this neuron didn't have any effect on the subsequent part of the network, right? So it's, again, the idea is that, I don't want any single neuron in the network to be super critical. And so if I have some fraction of dropout, it was experimentally found that if I have some dropout in my network, it makes the whole network more robust. It's a kind of regularization, right? So this reduces, overfitting and overdependence on single neurons and so on. So again, you'll see in your neural network parameters or in a paper, we used X% dropout, right? That's just what it means. And then kind of finally, another kind of critical idea is what are called residual blocks or skip connections. And so if you ever heard of this network called ResNet, right? So ResNet was like the thing that popularized these residual connections. And it's a very simple idea again, right? So the idea is that if I've got some sort of input coming in, and this goes into, some set of layers to produce some sort of output, what I could do instead would be to have like a little extra highway where instead of going straight to the output, I can bypass these layers entirely, and this is called a skip connection. So it's kind of like saying, if it turns out that what I really need over here is just like the identity function, for example. I just need to pass the input directly through this layer, and I don't want to spend thousands of parameters learning the identity function in this layer. I could just kind of like add these little extra highways. It's kind of like the way that you read it is kind of along the lines of saying, the network should know about information from earlier layers without having to have it processed, right? So a lot of times you'll see these little extra highways from lower levels of the network over to higher level blocks, and that's all it means, right? Okay. And I guess the last thing I would say is that, we talked about a bunch of different architectures. We talked about a bunch of different, attitudes towards optimization and so on. Kind of the final thing that you have to deal with in the real world is what's called hyperparameter tuning. Right? So for example, what percentage should my dropout be? What should my learning rate be? What should my, whatever. There's like often a lot of little design choices that you have to make in a neural network. And instead of you manually trying to go through a bunch of possible ideas, and in addition to the actual numerical parameters, there may be architectural parameters, like, should I use, 2 layers or 3 layers, or should I use, 100 neurons or 200 neurons, right? So there's like changes in the architecture that you're also maybe wanting to explore, and you kind of, in some sense, want to do kind of like, depending on how these numbers are parameterized, you almost kind of want to do some sort of meta gradient descent on the hyperparameters to find the best hyperparameters to make your network perform the best, right, at the downstream end, right? And so that's often part of the secret sauce of making something work is this, you don't just choose one thing and fire and forget it. You're constantly not only optimizing the weights and the biases, but you're also optimizing the big picture of how do you structure the network and what choices do you make in the optimization, right? So the whole thing is just like, to me, magic, just like there's a zillion choices to make, and a lot of times they only can be made based on your intuition from having trained a bunch of networks before, right? So it's just like, there's no real advice I can give you that's gonna make this process any easier other than starting to do it, right? Okay, so let me pause and ask, any questions or comments about what I said so far? Yes? Say that again? Is the operator a concatenation or an addition? Is that what you said? I think it can go either way, right? So I think that I've seen it where you just add the things directly, like for example, like I guess it's not quite the same thing, but it's like in a positional embedding, you add it directly. But I think it also can be a concatenation, right? Yeah, I think it will make a big difference, right? So I think the way I drew it this way, that's a good question. Does anyone have an opinion on this, whether it's concatenation or addition?
So for me, I think the resonance is basically try to avoid when you step too many layers. So we try to avoid the gradient vanishing or exploding during this process.
Right.
And then the reason why they try to add this flywire into the
right.
next layer is because they try to avoid the information loss
right.
because of the deeper layer.
Yes,
really
but his question was, is it addition or not, right?
So in the original paper, it should be addition.
It is addition, right? That's why I drew it like a plus, right? Yeah.
Yeah, if this part is like just generating which were all 0, you can do this flywire.
Right. Okay. Yes. So we agree addition is typical, right? Do you have another comment to that? No? You're nodding along, right? Okay. All right. So that's basically so basically I wrote this lecture. One of my last lectures I wrote in the summer was just like going back and thinking about, okay, so what do you guys need to know based on all the stuff I want to talk about in terms of what's coming up? And for me, that's kind of like the salient stuff, right? So let me just say that obviously, so again, let's come back to the big picture of the course, right? So this course is computational creativity, right? Which means that I'm interested in, for example, how are artists using these tools to generate images and art, right? So clearly these people are not deep learning experts, and the reason that it's possible for all of these non-technical people to be able to use these tools is that there are all these packages to make life easy, right? And so I am benefiting from those myself because I'm not a deep learning person, as you probably figured out by now, right? But if I look, so now I want to talk a little bit about, in practice, like what are some tools that you can use, right? So there's a zillion tools like you'll come across. There's Keras, TensorFlow, PyTorch. But then there's also these super easy tools like Jupyter Notebooks and Collab Notebooks that make your life easier when you're trying out things, right? So for example, when I ask you to train a VAE on the first homework, I'm not expecting you to write this yourself from scratch. It's super easy to find something that will work, right? So for example, in the course, right? So if I go to my browser, so if I go into resources, the actual link to the book is to a GitHub repo, which has a whole bunch of notebooks for all the stuff we're talking about in the class, right? And so, earlier in the summer, it was like, I have no idea how to do all this stuff. So I just followed the instructions on this page, and I did pretty well, although I did need some graduate student assistance to finally get it to work, right? So sometimes what you're going to see me doing in this class is switching over to AnyDesk. So AnyDesk is basically like a remote desktop thing. So here, I'm just coming over to my good computer over in the background. I'm wondering, oh yeah, now I have to manipulate because I have like 2 desktops, right? So let me just kind of like look here. So you can see that the GitHub repo talks about this thing called Docker, right? So I learned about all this stuff. You guys probably knew about this like when you were kids, but for me, Docker and Conda and all this stuff was totally new, right? So Docker is basically just something that it's kind of like a container on your desktop that has all the stuff you need in it. And part of the problem with all of these deep learning things is that someone will write a paper or an algorithm and they'll write it with the most up-to-date libraries that they have at the moment, and then 3 years will pass by and all those libraries are out of date, right? And so you don't want to take your own computer and downgrade your hotness to like the version 3 releases ago, but you still want to be able to use this code, right? So instead what you do is you use this Docker container that contains basically like a virtual machine of just like the stuff that worked at the time. And so for example here, let me just see if I can get this to work. So here, oops, sorry. Why is this not auto-completing? OK, I'm doing it. All right, so I have the stuff on my drive. And now what I want to do is, since I always forget, I have to go to the web page and see what I need to run this. So since I have a GPU on my machine, I can run this part here. And where did my command window go? Here it is. And then what happens is that the thing is running in my web browser, hopefully. And so now I have all these neural network notebooks, right? So if I go back to here, I can see that for every chapter of the book, the author has very thoughtfully put together these nice repositories. And so now I can basically run these examples just from here, right? So if I want to, how do I do this? It's so small in my field of view here. Oh yeah, here we go. Restart. OK. So now I'm kind of like starting from scratch. And what I want to do is I want to just run the whole thing. And you're all laughing at me because I don't know what I'm doing. How do I do this? Well, I guess it's working. So, but somehow I undocked the window, which is not what I wanted to do. How do I get this back? Whatever. You're going to come up with a bunch of errors here that generally don't seem to matter. Here, for example, again, it's too small to read, but you can see that with only a few lines of this built-in code, right? Like there's about 33 lines of code here that has suddenly built this huge 500,000 parameter neural network, right? 600,000 parameters. You can see it's got choices about convolutional layers, what activation function is being used at each layer, and so on. And then you just kind of hit the button that says train the model, and it starts to go. And you can kind of see here that over time, the epochs are increasing, and the model training is getting better. I'm not sure why it stopped here. Or maybe I didn't stop it, right? Train the model. Here's the model. Is it training? Yeah, here we go. So now it's training, right? Now this is a machine that is pretty good, right? It's got, what is 24 gig of RAM? Is that right? Yeah. Right. And a 4090? What is the graphics card we have? 3090, right? So I mean, this is like a good gaming rig, like a $3,000 gaming machine, basically. And so this will take, I'm not going to let you watch it, but this will take probably a couple minutes, right, to train. Now, what happens if you don't have the great gaming machine, right? So let's switch over for a second to back to my browser on my local machine, right? So here, this is my laptop. I clearly don't have any sort of computational power on this machine. And so what I could do is I could just like Google variational encoder collab notebook, right? So a collab notebook is basically like an in-browser way of running code, right? So there's like this notebook here. And so it looks very similar to what I did before, except it's not running on my local machine, right? It's running somewhere else. And so if I, just like want to get going on this, run anyway, this is using free computational resources on Google's machine somewhere, and I'm not using up, my own memory. However, eventually you will come up against limitations where, maybe you have to spend more time or more resources than the free version allows. And in that case, you can always basically, where is it here? So I'm sure that they want me to upgrade, right? So where is it? All right, so it's like change runtime type connected to, so I can kind of change the, kind of type of processor that I'm running on. And then, one thing that might not be a bad investment if you find that you're going to be running a lot of code in this class is to just pay $10 a month and get access to, better computational power, right? So if you didn't buy the textbook, you could pay, $30 across your 3-person group and have more computational resources, right? That may be a decent trade-off to make. And so I'm very curious to know, because I have no idea, what as students you're going to be able to find that will make this stuff work. Honestly, this is a learning experience for me, and so when we see how homework 1 goes, I'm very curious to know, what type of thing did you use? Did you use a Jupyter notebook on someone's amazing gaming machine? Did you use a collab notebook and you paid $10 for it? Did you apply to use the RPI supercomputer and try to use their, parallel stuff? Let's see what works out, right? I don't know. And then that will definitely shape how future assignments go forward in terms of what seems tractable for everybody, right? I also don't necessarily want you to, tie up your gaming machine for the weekend when you could be playing Starfield or whatever, right? So, all right, and then let's go back and see. I'm not sure where we landed on this. I feel like there's still something running on this GPU because it shouldn't be taking this long. I ran this earlier, it was super fast. Sorry, are you still running something on the computer? No, he says. I'm pretty sure that when I did this earlier in my office, it took a lot faster. So I'm not sure. Oh, no, here we go. Now we're on epoch 9, right? But still, when I did this earlier, it was definitely 10 seconds per epoch instead of 20 seconds. But we're almost done. And so what I'm training here is just a simple convolutional network to recognize 10 classes of animals, right? So as soon as it's done training, then I can kind of see, the loss function is getting lower every time, the accuracy is getting higher every time, and then I can evaluate and see what happened, right? So I can kind of show some examples of, I know this is probably a little bit too small to read, but it's here's an example of a thing. What's the prediction? What's the actual thing? So here, the middle, this guy says prediction automobile, prediction ship, prediction ship, actual truck, right? So it gets it right sometimes, it gets it wrong sometimes, but it gets it right definitely more often than it gets it wrong. And so again, for me as a graduate student in the late 90s, even this would have seemed impossible, right? To train a network with 600,000 parameters in 3 minutes, that would be crazy to me. So things have really changed. And of course, this is the simplest possible neural network that you could imagine trying to run, right? So you guys are living in a truly different age than I was. So like I said, when I do our lecture next time on variational autoencoders, I'm going to be showing the book VAE examples because I know that they'll run on the machine in my lab upstairs. But you can see whether those book examples are going to run on the machine that you have or whether you need to find another machine. The other thing I'm going to say is that this is where some sort of programming or at least Stack Overflow knowledge is important because if I go back to you can see that these purple links tell me that I've tried to run these things before. Right? So here's this variational autoencoder. Yeah, this looks fine. So then if I try to play this, I get some error that I don't understand. Maybe you guys understand this, but wheel pep 4 or 5 tags, I don't know what this means, right? So I just found another collab notebook that did seem to work, right? So you can probably figure out what some of these errors are, but not every notebook that you find is going to work out of the box either, right? So surprisingly, even though the whole point of this Docker Conda thing is to not have these kinds of dependency problems, it still seems to happen all the time, right? So I have a student of mine that graduated with a PhD a few years ago, and now she's back in my lab. She says, like, whenever she starts a new project, it seems like the first week of the project is like debugging someone else's notebook to try to make it run, and then modifying it for what she needs, right? So don't be discouraged if it doesn't work, the first time. That's another benefit of having a team, is to help, whatever it is called, like active coding, right? Active debugging, right? How can we get this to work? And this is, again, what I want you to share your experiences on the Discord, right? So this is not a competition where you're not giving anything away by sharing, hey, I tried this collab notebook and it didn't work, but then I made this change and it worked, right? That's the kind of activity that I'd like to see people sharing on the Discord, because you're not competing against each other on who can get the code to work, right? That's not the point of the class, right? And like I said, I also want to be clear, just like we were talking about last time, is that I am interested in your experiences taking these pictures and trying to generate results, right? I'm not going to flunk you for your autoencoder not working, right? In fact, part of the point is that as we go forward with more and more advanced models and algorithms, your first VAE is probably not going to make very interesting or good results. Like if you're doing things, I started someone talking about Lego bricks, right? Your Lego brick example may generate things that look vaguely like Lego bricks, but not like pictures from the Lego catalog, right? And that's okay. And again, to get things to work, you will definitely have to significantly subsample your images, lower the resolution of the images. You may be dealing with 64 by 64 images in the beginning just to get something to run, right? And that's okay too, right? So my goal is to encourage playing around, sharing your problems, trying to figure stuff out. Because again, when you see, and this is again, one of the reasons why you see me drawing these goofy diagrams by hand on paper, is that I feel like it's so easy to teach a course like a deep learning course, where you just have a pre-made PowerPoint that has all these network diagrams on it, and you flip past them, and it seems like, oh yeah, this stuff just works right out of the box. I know it doesn't work right out of the box, right? So this is a more hands-on sharing experiences kind of class than maybe you're used to. So that's my ending of the preaching. Okay, any questions or comments? All right, well, with that, I will stop the recording.